Hi guys, welcome to week 9 workshop. Sorry about the confusions. Um, so it's here is supposed to be a workshop on week 9, not computer lab. So if you go to Moodle and you go down to week 9 and download this workshop week 9 problem here, um, then you will open up this PDF file. It's a week 8, just ignore it. It's actually week 9. So in this week, we're gonna be solving through two problems regarding to pedestrian flows. So the first problem will just be a simple problem with just 3 pedestrians. This problem will introduce you to pedestrian flows and make you be more familiar with at least definitions. And the second problem will be using real data. So if you go to this URL, this is the archive from the lab that was experiments a few years ago. This we're gonna be look into like a more real data and a lot more information, but it's based on the same idea. So we'll use the eddy extended definitions for flow and density. And this I will show you in Matlab. The first problem is simple. I'll just show in Excel. So hopefully you guys can follow easily. So let me start off with, so this problem we have, we want to estimate flow, speed, and density of this pedestrian data for so we have the the region that we want to estimate the value is this region. So here, if I just copy this table into the Excel, just like this. Something like that. So if you remember the lecture, we talk about eddy's definitions, that the pedestrian flow, the flow is actually the sum of all the distance that travel by pedestrians divided by the regions of the observations that we're interested in. If we do in terms of dynamics, if it's across different times, then this T is actually the time step that you actually measure. So, and the density, where's the density formula here? So the density formula is a sum of time that people spend in this area divided by this is the total time that you observe times the regions, the areas, width,คูณ length, pretty much. So we're gonna be using this two formula, or yeah. So this is this exact formula that we're gonna be using it. Since we're gonna be using we call this a discrete problem that we're doing like step by time step. It's very easy to understand, I think, and so that's why we need this t as a time step for each time. So what we can do here, we can calculate the distance that people travel for each time period. So obviously from 5 to 6, let's do here. We start from 5, so just ignore the first frame. We start from this frame 6. So the distance is square root of the difference between x square plus the difference between y square, and we can do this. Let me put this line to top order. Yeah, so we can separate different people. Does that help? I hope it does. Yeah, so this is the first person, and the second one is here. We ignore the first frame as we did. So we're going to be using that. We perform the same thing here. So that. So these are the distance that each ID 1, 2, and 3 travel for each time step. From frame 5 to frame 6, this ID 1 travel for 1.4 meters. From 6 to 7, he traveled for 2.2 meters. Same as the 7 to 8. Same analogy for this second pedestrian. So from 6 to 7, he traveled for 2.2 meters, and then he walked faster from 7 to 8. For this third pedestrian, so he sprint at the beginning, he's going really fast, and then he slowed down after that. So these are the distance. And then the problem setup is we have a measurement area that we're interested in. So we can say the region has, let's put it like this. So we have min, let's do x here, let's do min and max. So min is 102, and min for y is, min for y is 100. 100. Max for x is 102, max for y is 102. We can just plot this coordinate. So let's do this. So I put scatter here. This is for the pedestrian 1. I will add select data. I call this ID 1, and we can add ID 2. X for ID 2 is just here, and Y for ID 2 is here. And we can add ID 3. And here's the X for ID 3. Here's Y for ID 3. We can design strap type thing. Yep, that will be better. Yes. So now we have this line to connect this dot, so we know that the trajectory for each person. We can put in legends on top maybe. So ID 1 start from here, and then he walk up northeast, and there's ID 2. So he start from 104. So he start from east, and he travel southwest like this. And ID 3, he start from 98, so he start here, and he also going northeast as well. So and then we can plot, we can create this region box that we're interested in. So let me just do 100, 102. Uh, 102, 102, 1. So let's select the region. Yeah. Let's do 100. Let me do that. Change charge time. Scatter. Yeah, let's do that instead. And here I think chip on I. Let's do like that. Yes. So this dash box is the area that we're gonna use the measurement. So this is the area that we're interested in. We're gonna observe in this area. So here we know the distance. So if you look at this, so this is the formula that we're gonna be used for calculation. So let's do density first. So density is the time that people spend in these regions divided by the time steps, total times of the measurement, and the area. So this A is 2 times 2, so it's 4 meters square. So let's do okay, time in the region. Oh, first, we need to know that each time frame, we can check if they are in region. So we're gonna create this column so we can check that if this frame, this coordinate that we measure, if it's inside this box. So what we can do is we're gonna use multiple conditions. So what we can check is this more than or equal. So it has to greater than the minimum, but it has to be less than the maximum of x. And y has to be greater than or equal minimum of y. Look at this. And it has to be less than or equal the maximum of y, like this. I don't think I need this. Yep. Okay. Try this. Yeah. So what this show is that for this time step for this pedestrian one, he is within the region. Yes, because he starts from this point, right? And then after that, um, from reach from time step 2 at frame 6, he is still inside, as you can see from this plot as well. Yes, he is still inside, but the third frame, which is frame 7, he's already outside, so he's already traveled outside. So the idea is that we're just gonna consider him inside for frame 5 and frame 6, but not frame 7 because he's already outside. Yeah. So that's what we're gonna do. Actually, I think this makes more sense if you do this. Because the last frame is, we don't really travel anywhere, right? Yeah, I think it makes more sense if we do this. Because we just measure the distance for frame 5 to frame 6, 6 to 7, and then we stop the last frame, the last distance is at 7 to 8, so 8 is not gonna go anywhere. So that's when he stopped. Yeah, I think that makes more sense. So we're just gonna do this. And we have this. So we have this check if they are in the regions. So we can calculate total time that. So we can it's called time for each frame. So the time for each frame is 0.1 seconds. We can say total frame is from 5 to 8, so it's 3 frames. So the total frame from frame 5 to frame 8 is 3 frames. So that's the total time is 0.3 seconds, right? 0.1 times 3. So we can say time that people spend in these regions is count. So count how many truths. Wait. Oh, no, I think we can do some. Okay, never mind. Count if and if they're true. Okay, so there are 3 frames. So pedestrian 1 is in these regions for 2 time step, right? For 2 frames. And this pedestrian 2 is not inside this region at all. And pedestrian 3 is inside for frame 6 to 7. So I just lead 3. And you can multiply that by time for each frame. And then we can calculate density like this. So the density is this, the time that people spend in these regions divided by the total times. This capital T, which is 0.1 times that 0.3. That make this capital T, and then this A is that time bracket is minus that. So the density for this 3 time frame is 0.25. Now we can calculate the flow. So the flow is the sum of all the distance that's traveled by pedestrians divided by capital T and A. So we need to find the total distance that's there inside. So distance in the region. So the distance is sum if. So we're going to be summing this if this is true. Wait. What happened? Sum if range, yes, this range of the sum. Oh, no. Range to check, and the criteria is true, and sum range is this. Five point 5.06. 1.4. So for 3, start from here. And then we can calculate the flow from this distance divided by capital T, 0.1 times 3. And then don't forget the bracket. And then we can do the distance, the capital A here, which is y minus y minus, okay. And the flow is 4.22. Notice that there is there could be a bit problematic here. If you look at for this, A should not be that bad. Like from frame 5, right? Just look at this pedestrian 1. So this is distance he traveled for this frame 5 to frame 6, which is 1.4 meters. And then from frame 6 to 7, he actually traveled 2.2 meters. But the distance that he actually spent inside is actually half of it. So if you want to be more precise, instead of just sum of this, if you look at this, right, you might want to divide it by 2. So the same ideas go for pedestrian ID 3. So if you look at him, first iteration, he starts from this point, and then at the frame 5 to frame 6, he is outside, but at the end, at the frame 6, exactly that, he is inside these regions. And from 6 to 7, he spends time inside these regions, just briefly. And oh, sorry. Uh, this pedestrian ID 3 is actually start from here. So this first time step, he outside. And the second one, um, the frame 5 to 6, he's start from outside, and then at the end of frame 6, he's inside. So the time that he spent inside is actually between 5 and 6, but we don't detect that. We detect when he's inside at frame 6, and frame 6 he's traveled for 1.4 meters. But at frame 5, he traveled for 4.2. So we capture this distance in frame 6, right? But in reality, the distance that is traveled is actually here. So if you want to be more accurate in this, you can either reduce the time step instead of 0.1 second, maybe 0.01, and we're gonna get more detailed coordinates. And this error will not happen. So I just want to remind you that yes, there is some error. Depend on your how big of your time step that you made. The more coarse time step that you create, um, you prone to have more error. That's normally happen. So more time step will be more accurate. At the same time, it come with more computational requirements. Like instead of uh, this just 9 rows, it could be twice as much or something like that. So it's a trade-off that you have to make. So, but you relatively get the idea of what's going on here. Um, so we know the density, we know the flow, then we can calculate the speed. So from fundamental, uh, relationship, speed is flow divided by density. So you can do that to get speed from FD, from fundamental diagram. Or you can, you know the distance and you know the time for each frame, you can just average this. So maybe you can do speed like this. Uh, instant instantaneous speed, instantaneous speed. Um, that divided by oh, that, then you can just average. Yeah, so this is the average speed um, from the entire. Now we don't have the regions that we calculate. So this speed come from just the entire populations, the entire simulations. We don't consider just these regions, but this speed is come from the relationship between flow and density that we measure within this region. So that's why they're a bit different. In this case, we don't consider this second person at all, right? As you can see, because this orange ID2, he doesn't cross into this regions that we're interested in at all. And he's actually walked really fast. Like in this time step, he's actually walked fast. So so we don't capture that here. Yeah. So um, is that everything? Speed, hypothetical. Yeah. So that is the idea for this first problem. Hopefully you understand how to do it. You can do this in more systematic way in MATLAB, for example. Now let's look at problem two. So if you go to this link, this URL, so in this experiment, they did a few setups, like quite a lot actually. So they have participants wearing hats, and then they have camera in different angles, and then those camera are tracking the positions of each person's, and then as different frame, you can extract their trajectory, similar to what happened in this table. But when you have a lot more participants, a lot more people, it's a lot more complicated. But it's the same idea. And they have different setup. They have single files. They have bidirectional flows. They have some obstacle. They have some bottleneck that people do. They have some cross flow. What are we gonna be interested in this concern bottleneck? So probably this one. So here, if you click to concern, in this setup, um, they have um, they have these pedestrians starting from the left here, and then they go into the right, walking from left to right. And as you can see here, there is the width at the beginning, and then the width got reduced by these W parameters, and then they have a few setup where they have 1 meter width and 2 meter width. So they want to observe the bottleneck of how that's affect to the pedestrian flow. So yeah, so you can observe the bottleneck here. So what you can do is you might want to set up a measurement area around this area. You can observe before the bottleneck and after the bottleneck um, as well. So if you come here and uh, we're gonna download two files for 1 meter. You can download the camera, or what we need is text files, B100 combined, and this B200. So you right click and save link as, and then there's this text file. I already saved them. So if we come here, so if you open this, so this is the experiment. So people wear hats, and then there's this camera that's tracking them. So they want to observe this bottleneck right here of how people behave, like what congestions look like, and their flow and density. As the bottleneck is widened, what's gonna happen? Um, wait. Oh, I think they are the same experiment. Oh, I think both of them are 1 meter wide. So yeah, so if you want to watch 2 meter, just download this. But oh, they have two cameras, so both of them are 1 meter wide, but just from different angles. So, but I just download this 100, B100 and B200. Just this file and that file. That should be enough for us to um, some another researcher did the image processing, computer visions, and they already extract this trajectory for us. And those trajectory are recorded in these two files, this B100 and 200. So for example, this person one, right? This first person at frame 275, he is at these locations. And at frame 276, he is at this location. As you can see, it's the more sensitive your camera, like, I mean, the more FPS, the more data is gonna be, and the more details your outcome is gonna be. So if you use a good camera that's capture like 60 or 100 FPS, then you're gonna have a lot of rows here. So I already wrote Matlab codes. So I'm just gonna run through this with you. So here so here at the beginning, what I do is well, I clear all the existing data. As you can see, I clear everything from this workspace, or if there's anything open, I also close them. Yes, close all. And then first I extract this data for B100 combine.txt. Yeah, so if you run this, you can see the data here is open in this workspace. Oh, my workspace looks a bit weird. Okay, that's fine. And then I convert that from this to this ID and frame. And then we can set up a measurement area, like we did in the previous questions. And here, so for each frame is 0.16 seconds, and then each interval is 30 FPS. Wait, hold on. Oh, I think the camera has captured 30 FPS. Time for each frame is 0.16. Does it specifically say anything about this? How do we come up with this number? So each frame is 0.16 seconds. So it's 6.25. Okay. So it'll be, yeah, I will find this out. So here, if you go to this cell and you press Control Enter, it will run this from line 12 to line 25 here. Just run this entire cell, and this window gonna pop up. And what we see is the blue dot are each person's at this frame 286, and this red regions is these regions that we set over here. You can increase, you can decrease the size, you can change locations, and here, okay, let me run through this maybe. So we create a figure called figure 5, and then we extract the x value from the data frame, which satisfy this condition that the frame, it must be in frame based on this index. So start from frame 286, that's the first frame. And y, do the same thing for y. So now we got x and y, and then we can do scatter plot for all the points that we extracted. And then this just write the titles, the frame. Yep. So that's a title. And then we can plot this region, this red regions. So we plot, and then we set the x limit. So x start from -300 to 300, also same as the y, and then pause. So what this pause does is it stops this iteration for now. But if you press any button, it will go to the next iterations. Oh, I see. Okay. So this F interval, you can play around. You can change this. So what I code was one press, it will add 30 frame to this and then recalculate every positions. You can change this. If you lower this number, each press is going to change less, and you're going to see more detail. But here's basically what happened. So yeah, let's play around this. So I will change this to be 10 instead. So if I try that again, so Control Enter. So here, so each time you press any button in your keyboard, it's going to change just 10 frame. And you're going to see more movement, more detailed movement. Right? So yeah, so that's what this frame does. And this is the time for each frame, 0.16 seconds. So yeah, that is for this cell. Is to just show you the plot of the data overall. But that's not what we're really interested in. We are asked to create fundamental diagram for two cases. So similar to what we did in the previous example, we can calculate density, speed, and flow from this. So what this does is ID. Oh, right. So here is calculate distance for each person. And then we can check whether this person is in that area between the frame. So before we run, I want to make this smaller. Can I dock this? Never mind. Let's do this. So here, before I run, you can see we have 4 columns and 84,000 rows. It's quite a lot of data. So for each run, it will go to each ID, so to each person, and then it will calculate the distance from. Okay, so what I did was the first time step, there's no movement, and then we calculate the distance at the end of the movement. I see. So similar to what we did in example in problem 1, we calculate dx, the change in x coordinate, and change in y, and then we calculate distance from square root of x squared plus y squared, the different delta x plus delta x squared plus delta y squared. We got distance, and we can do this check if it's in the area. We can do this regions if X for this person is greater than the minimum value of X value in regions and less than the maximum X value of that in the regions, greater than smallest value of Y min for that region, and less than Y max of that regions. And from that, it's going to be true or false here. It's going to be true or false. And then if you write that check if it's in the area um, in another column. So if you run this, you can see we create two new columns. This distance is the distance they travel at the end of each time. So like this distance is from frame 275 to 276. This from 276 to 277, and this regions is to check if it's inside the box that we're interested in, the regions that we're gonna do measurement. So as you can see, a lot of them are outside, but in this brief period, this guy is inside this region. So if you increase this region size, you can expect more true in this column. So we did this for all the people, all the participants. And here you can calculate density and flow. So we can calculate distance, similar to what we did. If it's inside the regions, then we sum them. If they are outside, then we don't care. So if we sum the total distance divided by the area times time frames times time interval, that's gonna give us the Q. So this is the flow for each time step. Similarly, we did the same similar thing for density. So instead of calculate the sum of the distance, we measure just the size of the distance. That means how many trues are there, how many people are inside that region. So that can also so the formula is actually the formula is count of people inside, right? Oh, okay. So the sum of the time divided by the time step times the regions is actually this sum t is the sum of people inside times. So times can cross out, right? Because they are both just the time step of our each the time gap between each time step. And so you just count up how many people inside these regions divided by the region's area. And that's basically what this formula is. So we did that. We can calculate Q and K. And then we can plot fundamental diagram. And this is look like this. So you can do speed equal Q divided by K. Should work. Okay, I should do this. Hold up a minute. Why is it 2 by 2? Oh, it has to be element wise. Like this. Yep, that's look more like it. So we can plot speed density maybe. Plot speed, which is V, and density. Let's close that first. That speed and density, it looks pretty bad, huh? It should have this curve like this going down like that, but what we can do is if we can increase these regions. So instead of this, we can do -50. So we can increase these regions. That's not significant. Let's do 100 and 100. Okay, can do that again. Now we're talking. So here, I made this longer. It's the same width, but I just made it longer. As you can see, the longer the measurement, and then we can um, do the same thing. We'll calculate the so here this cell will calculate the distance and check if it's in the area, and then we can do calculate density and flow. Then we can plot FD. Now look a bit better. Scatter, density and speed. Sorry, that's B. K and B. Yeah, it looks a bit better. So here we have so if you increase the size, the data is gonna be less fluctuated. So it will look a bit better. So that is the fundamental diagram for width of 100. So if we change this to 200, and if I do this, and I can do the same thing. Let's do this. Let's do it 30. So we take this data from another experiment. That's the width increased to 200. As you can see, the width is wider, and that's the data. If you want to stop the operation, like what I did here, once you close the window, like for example, you have this window here, you want to stop, you just close it, and it's still running, it's still waiting for the commands. So if you press anything, the window gonna pop up again. But if you want it to quit, just Control and C, and then that's just gonna stop these operations. Okay, if you come to this cell, we can do the same thing. This one calculate the distance for each ID and check it is in the area. Then we can calculate Q and K. And then we can plot fundamental diagram. So that's what it looks like. So as we expected, so the wider the corridor is, we expect more flow, and the data is not as messy as before because we create this region to be a lot wider. If we reduce the size like this, we can expect this graph to look a lot more messy. So yeah, you can play around with that and you can try them. But that's basically how you did this problem too. These are the fundamental diagram for two cases. Maybe I can keep this here, and then I can do this. I don't want to close all because I still want that. Okay, I don't want to run this. Come on. Let's do figure 3. So this is so this is from this figure 3 is from B100, and this figure 1 on the right here is from B200. From the look of this, the flow are not that different, so the fundamental diagram actually looks very similar. And the density for here, the critical density is about 3 here. Here is about 3.5 or something. Critical density for 200 meter wide is actually higher than the critical density for this. 3.3. About the same, huh? Okay, yes, here's more fair comparisons. 1 meter wide, there's higher density data over here as is cluster over here, whereas for the width 2 meters, that's not as dense, people has more space to walk, and the flow for this 100 meters, 1 meter wide is the capacity is actually higher than for 2 meters. And that's what you can conclude from these two fundamental diagram comparisons. And that's it for this week demonstrations.